In this video, we're going to go over the Grass Waterway tool. Previously, you should have already ran the More Terrain Derivative tool, as those outputs will be needed to run the Grass Waterway tool. Grass waterways are strips of perennial grass planted along areas of concentrated flow, and they really help with preventing gully formation and capturing some sediment before reaching the stream or ditch further downstream. So let's take a quick look at what the Grass Waterway tool asks for. First, it wants our field boundary feature class. Second, our stream reach feature class. And then it's asking for the stream power index, which we produced when we ran the More Terrain Derivatives tool. You'll remember that when we ran that tool, we had the choice between a filled or an unfilled DEM. The tool help over here goes over the differences between that again as a little refresher, but we're going to talk about that in a little bit more detail. I also want to mention that once you supply your stream power index, you have a decision to make what threshold you would like to set for siting grass waterways. You can either choose a threshold by standard deviation, that's above the mean. You can see we have a few options between 2 and 5 standard deviations. Or the user can supply an actual stream power value from the roster. And then optionally, you can also include depressions. If depressions are included, no grass waterways that intersect a depression will be in the output. So before we run this, let's just take a closer look at those specifications. So as I mentioned in the video for the More Terrain Derivatives tool, it really matters which DEM you use to generate that stream power index roster. Once again, here are the differences between using a filled or an unfilled DEM. You can see in this example, in this extremely pocky central Iowan watershed, that using the filled DEM, all those depressions just got filled, and so flow was able to go right across them, where when you use an unfilled, the flow paths stop at every single depression. So just to reiterate, it is important to be aware of your inputs and the impacts it could have on siting conservation practices. The second thing to pay attention to is how you specify the stream power index threshold. One option is to say how many standard deviations above the mean you want it to be before a grass waterway is sited. You can choose between a range of 2 and 5 standard deviations, taking a half a standard deviation step each time. And this considers the mean of the stream power index roster, and this is of the entire roster. So if you remember, these rosters actually expand to a 1,000-meter buffer beyond the watershed boundary. So these values can vary a little bit and may not be as accurate as you're looking for. It's up to you. The second option is to have the user specify an actual stream power index value. And this will take some time to look at the roster, see the distribution of values before you make a choice. And remember, your stream power index range is going to vary depending on whether you used a filled or an unfilled DEM. Alright, so let's go ahead and run this tool. We'll put in our field boundary first of all. And the stream reach is automatically added, and you can see I have an error that says, hey, this doesn't exist. But if you remember in the previous video, I named mine to designate which DEM I used to generate it. So I just go over here, grab my SPI that I've given this name of _fill, drop it in. If you stuck with the regular naming convention, you didn't get that error and everything's fine. Alright, so we need to move on to our selection method. I am going to go with the standard deviation threshold, but I'm going to up it. Personally, I've found that when I use 3 or lower, that grass waterways just get sited absolutely everywhere. And I would like to have the best suited location for grass waterways. So I up my threshold to sort of say, give me these optimal regions where the SPI value is very high, therefore gullying is an extreme risk. So this is why I up it. Feel free to choose whatever you'd like. I recommend running it a couple times to see the differences you get in your results. Next we have the optional depressions, which I most certainly am going to include since I ran it with a filled DEM to get the stream power index. Remember, if you include depressions, nothing's going to be sighted through them. And then we have our grass waterway output. I'm going to change this name a little bit to represent my inputs that I chose. So I generated these using the SPI value that was derived using a filled DEM. So I'm going to put fill, and then I'm going to put 4SD, indicating 4 standard deviations used as the threshold. Again, this is just for record keeping, similar to what I did in the more terrain derivatives video. Then we hit OK and let it run. So while the tool is running, let me give you the lowdown on how it actually works. First, it's going to take qualifying SPI values. That's any value that's greater than that standard deviation. And that's going to be smoothed with a majority filter. Whatever is remaining, those cells will then be expanded to improve overall connectivity. And then it's going to be thinned back down to 1 cell's width. Those remaining quote-unquote lines are then going to be converted to a polyline feature. Line features shorter than 50 meters are going to be deleted, and this is just for practical purposes. And then a stream reach feature is going to be masked out, and that's just to make sure that we don't have a very long grass waterway being sighted all the way through the channel. Finally, only outputs within isag equals 1 field boundaries are kept. That's right, for this tool, pasture is excluded. Alright, so the tool is just finished running. You can see it's been automatically added. And I'm going to add some color just to make them stand out. I'm also going to increase the thickness a little bit. Hit OK. Now we can see we have a few placed along the landscape here. Some quite long ones too, which is good. And then we can zoom in around, take a closer look. If you look at it with your hill shade, you'll see it makes sense where some of them are placed in these lower areas at the bottom of slopes, which makes sense. Let's take a look at our attribute table. We can see that they're associated with a field boundary ID. So you may be looking at some of them and say, but wait a minute, doesn't that cross a field boundary? Let's look at this one. But they've actually been split up by the field boundary. So if I make this my only selectable layer and select it, you can see it doesn't just continue on through that field boundary. These are 2 separate features. So we could look at it by field boundary, see how many are sighted per field, and then we also have the length of each grass waterway within that field. A nifty thing you can do with your grass waterway output is prioritize it by the runoff risk assessment. So as you saw in the attribute table of the grass waterway output, we have our field boundary ID, which means that we can join our runoff risk assessment to our grass waterway output. So let's go to join. We'll choose our runoff risk table. We're going to join by field boundary ID. And we'll hit OK. Then let's go into Symbology, go by categories, and runoff risk. We'll add all values. We'll keep null as a green color. We'll make very high red. High as, let's just do orange. And then present, we'll do yellow. So we'll notice that we did have a critical field before, but none of the grass waterways got sighted in that critical field, but that's okay. So now we get an idea of the priority of these grass waterways, where they may be most effective. So these red ones, for instance, may be more helpful with preventing gully formation and other erosive characteristics compared to the ones in yellow. And this is just a different way to visualize and assess this output. Here's a brief recap on the grass waterway tool.